Now we're going to come to sort of the heart a little bit of the course and start talking about software for optimization modeling, and then in the afternoon about optimization solvers, and then you'll get some hands-on experience at trying this out. So the nice thing about optimization is there's a rich set of modeling languages, and I showed you a little example of an AMPL model that looked very natural. I'll talk about some classes of optimization solvers, give you a very brief introduction to AMPL. You're not going to learn a programming language by listening to a lecture. I don't know if you know this, but that doesn't work. You have to have hands-on experience, so we'll have that for you in the afternoon. When I was at the University of Dundee, they had a course on Fortran 77 on a blackboard. And I acted as the compiler for the lecturer because I would spot syntax errors on the whiteboard. So similar to what you did yesterday to me, I was the compiler. So we're not going to try and do that here. So algebraic modeling languages, or DSL, which stands for domain-specific languages, have some really nice advantages. One is they allow you to express optimization problems in a very natural way and a very rich way. So you have nonlinear expressions, integers. You can expand these modeling languages as well. You have access to something called automatic differentiation, which is a technique that computes exact gradients, or gradients that are exact to within unit round-off error, at a cost that's proportional to about 3 times the function evaluation. So if you think about this for a moment, you could have a function of 1 million variables, and if you did finite differences, you would have to evaluate this function 1,000,001 times to get all the gradients. But automatic differentiation allows you to get the million components of your gradient in the cost that's roughly 3 times the number of function evaluations, assuming you have enough storage. So there's a slight caveat there. Basically, what it does is exploit the chain rule to provide gradients. It also has pre-solved techniques that sometimes reduce the model and make it more easier to use. There's a whole host of these modeling languages for optimization. AIMS is a nice one if you're a chemical engineer because it uses units and it is unit checking. So if you write an expression that has an equation, a flow balance equation, it checks that the units of the flows actually match up. You don't have mismatches in units. AMPL is the language that we use here. It was developed by David Gay, and it was one of the first, and Bob Fura, and it was one of the first tools that was written in C. So they worked with somebody called Brian Kernighan, who developed C at AT&T Labs. JUMP is a newer one that's a really nice language that's integrated with Julia. And there's modeling language Moselle and TomLab, which is built on top of MATLAB. So there's tools there that are very useful. But we'll concentrate here on AMPL. One of the features that I like in AMPL is that it allows you to expand the class of problems that you can solve. So AMPL is, you can think of it as it can solve mixed integer nonlinear optimization problems. It has complementarity constraints. But what it doesn't have, for example, is robust optimization or differential algebraic equations. But we built an extension to AMPL where we sort of added sort of operators like diff. And diff is just, this diff operator just does d of the function by dt, so, or of this variable by dt. So this is just a way of writing d by def by dt equals some right-hand side. And the back end of the solvers then does all the conversion and discretization. So it's a very convenient tool that we wrote and that allows us to write now differential algebraic equations in AMPL, even though AMPL doesn't know what a differential algebraic equation is, and it leverages all the automatic differentiation techniques. Here's a sort of short preview of some of the solvers and techniques for mixed integer nonlinear optimization. And we'll talk about branch and bound and branch and cut later. There's a whole host of open source and commercial solvers. The ones that you should be familiar with are Minel PBP, which is a very rickety and old branch and bound solver. It was one of the first mixed integer nonlinear programming solvers that was out there. It doesn't work very well anymore, but it's one that I wrote when I was a PhD student. Minotaur is a code that Ashutosh wrote with us when we were at Argonne and still being developed now at IIT Bombay. And Skip is a really nice tool by the Zusezentrum in Berlin. So those are some of the ones. And Pietro, I think, worked on BonMin, which is the branch and bound solver. Filament is another solver that I've worked on as well. And then there are solvers for non-convex problems. So this is sort of the second half of the talk. And the famous one here are, or the benchmarking ones here are really Baron, I think, and Quen. Quen is Pietro's solver. Baron is a competitor that was developed at Carnegie Mellon University. And again, Skip does some global optimization as well. One of the things you're going to want to do when you in the exercises this afternoon is you want to look for models in, when you write your own model, it's always good to start with something else. So here's just a list of some models that you can download, or model test problem libraries. The last one is in GAMS. I have some mixed integer nonlinear programming models. One of the cool things in optimization is there's this NEOS optimization server. So who has heard of NEOS as an optimization server? Okay, great. This is good. So do you like NEOS? Does it work for you? You're nodding. Okay, that's good. So NEOS is really good. I don't know if I can click on this, Pietro. It's not my laptop, so I can. Okay, I don't know what's going to happen next. Maybe not. Okay, I can't click on it. So NEOS server, and so that allows you to actually use all these solvers without having to have AMPL yourself or modeling languages yourself. This is run at the University of Wisconsin-Madison. The NEOS server was originally developed at Argonne National Laboratory by Jorge Mori and colleagues, and it probably solved hundreds of millions of problems by now. So lots of people use it, and there's a computational infrastructure for operations research, or COIN-OR, which grew out of a project at IBM and Carnegie Mellon University, and contains a lot of really good solvers, nonlinear solvers like IPOP, which is an interior point method. There are solvers for mixed integer optimal control problems, or the AMPL extension that I showed earlier. We're not going to look into this. And Sebastian Sager has got a nice resource there. So I'm going to give you a short introduction to AMPL, and Ashutosh will do a much better way this afternoon. So it's a mathematical programming language. That's the name, AMPL. That's where it comes from. It's an algebraic modeling language. You saw some examples. It links to many classes of solvers. So the nice thing is, once you've written your problem, you just tell AMPL which solver you want to use, and you can use a whole host of solvers. And if one solver doesn't work, you can use others. And that's really important often. It provides efficient first and second derivatives. You don't have to worry about differentiating your functions. AMPL will do that for you. And it's very efficient at doing that. And for the people who are developing solvers, so if you're somebody who writes your own software and wants to try it out, AMPL exposes a lot of structure of the problem to you. So it poses things like the integer variables, the class of constraints. So it tells you bounds and linear constraints or network constraints. It provides you with the sparsity structure, and it is extensible. So you can, even if you're working on a class of problems that are not currently covered in AMPL, there are ways of extending it and making AMPL work for you. So we did this for the mixed integer optimal control problems. We've also done it for robust optimization problems. So there you have problems where you have a constraint that has to hold for an infinite number of parameters, like one of the examples that we had yesterday, the circle that was described, the circular constraint that was described by the thetas. And those problems you can still, you can sort of put additions into AMPL that make it more flexible. And that's something that doesn't work with other modeling languages as easily. There are three main components that you need to write. There's a model file that describes the structure of the problem. So here are my constraints, and you saw an example for the uncapacitated facility location problem. That's just the equations. Then there's a data file that tells the equations what the parameters are, the coefficients, how many facilities there are, how many customers there are, and things like that. And then there's a command file that drives all of this, so that tells AMPL what to do. Another cool thing is that you can loop. So you can solve a problem once, but you can also, for example, fix a variable, solve the remaining problem, fix the variable at another value, solve the problem, fix the variable at another value, and solve the problem. So you could, in principle, solve an integer optimization problem by enumerating all the integers and solving nonlinear optimization problems in AMPL. That would not be a very efficient way of doing it, but it allows you to do these looping things. And sometimes that's useful when you're adding constraints. And then it has a link to all sorts of solvers, and you learn about some of those later. So there's nonlinear optimization solvers and mixed integer nonlinear optimization solvers. So this is just repeating the solvers. We don't need to, there's links to some of the websites and references where these solvers are developed. And in particular, you should try out this guy here that was developed at IIT Bombay. So here's a first, well, this is not the first model. This is sort of the second AMPL model. But this is nice because on the left-hand side, you have the optimization problem. On the right-hand side, the AMPL formulation. So it's a very simple problem that I made up. Is you minimize exponential plus xi squared. So that's a convex objective. And you have, this actually turns out to be a convex constraint as well. So there's a logarithm, a cube, and some bounds on the variables that are there. If you write this problem in AMPL, there's a slight change that you first need to tell AMPL what the variables are before you start building the objective function. Otherwise, it will complain that you haven't defined a variable. So the variables sort of go to the top. But that's OK. You can write your optimization problem in that way. And maybe we should rewrite our optimization problems. So the variables are up there. And this is just an index set 1 up to 3. They're non-negative and less than or equal to 5. And then I minimize the objective. And I give this objective a name. I call it F, because our objective is always called F. And it's written exactly as you see it on the left-hand side. So instead of this summation symbol, I need to write out that I'm doing a sum. That's I in or from 1 up to 3 and xi squared. So it's the same structure that you see on the left-hand side, which I really like. You finish each line with a semicolon. If you don't, you get an error. OK, that's easy. And then you have a constraint, which I call con. I should have really called it G. So this is maybe another mistake. This should be G, not con. But you can name your constraints any way you like. You can call them Sven or Ashutosh. But there's one thing here that the logarithm is not defined if x2 is 0. And the AMPL will throw an exception. So it will tell the solver that it encountered a nonlinear expression that it tried to evaluate where there was an exception, an IEEE exception was encountered. And it tells the solver actually which constraint it's in. So it tells you where this happens. So AMPL, if you started this from the default start, which we established this morning, default values are 0. That's just a convention. Then AMPL will not get very far if you solve this problem. But you can also give it initial guesses. And if you give it an initial guess that's non-zero, then the solver will converge for this problem. OK, so what you do basically, and you're going to do this in the course, is you're going to create a mod file. And then you start AMPL. And depending on what platform you're on, it's slightly more complicated if you're on a Mac, but I can help you with that. the first line basically said, reset is clear everything that you know that you have in your memory. And I just start every new problem with that word, because then I'm not going to have conflicts with other things that are already defined. And then I tell AMPL that there is a model that's called simple.mod. So this mod file is actually something that we can send you. I choose a solver, in this case IPOpt, but you could have chosen Nitro, and I solve. And then when you do that, I'm not going to show you what happens. A good thing to do then is it solves, it gives you some response, what the solver did. And then you can do something. This is a useful command, so display the name of the variable, its lower bound, its value, and its upper bound. So this is sort of a convention in AMPL that you can access variables and constraints with this underscore. And underscore con name, for example, for our problem, the constraint was called con. The variables were called x1 through x3. So that's the name of the variables. And this would just list the names of the variables, shows you what the values are. And if I didn't do it here because I didn't have AMPL, but if I did that, then AMPL would have actually complained that there was x2 was 0. So I can just tell AMPL I would like to initialize x2 to 1 and solve, and then it works. And you can choose a different number instead of 1, and it would still work. So that's a little example. You can get Lagrange multipliers or reduced costs out of AMPL. There's a slight, this is maybe slightly strange, that for a variable, underscore var gives you the value of the variable. To get the multiplier corresponding to the inequality constraints associated with the variable, you need to get the reduced cost. For a constraint, to get the value, you need to con.val. To get the multiplier, you just tell it you want con. So there's a slight, it actually makes sense, because for constraints, you're looking at multipliers so they're the dual variables, and variables are the primal variables. So it's kind of consistent in that sense. Last exercise of the day, and then you can go and have lunch. Gear train design problem. So you're given a gear ratio that you would like to achieve, 1 divided by 6.931. That's the number that was in the book where I got this from. And the way to get there is you translate x3 to x1 and then x2 to x4, and you gear them together. But your gears must have an integer number of teeth, so you can't have continuous gears. And so the question is, well, we can solve this problem in the afternoon in AMPL, if you like. You can set this up. But the real question I'm interested in is, can we find a simpler formulation? So can you come up with a simpler formulation? And this is only going to take 2 minutes, including copying it down and asking your neighbor what they had for breakfast. So you can, this is a very simple exercise. And I give you a hint. For this problem, you can do the expansion in terms of the one-hot encoding. But you should be careful, because it introduces a lot of additional variables. So I don't think that's a very good formulation. But, so my solution is simpler, but maybe not satisfactory. Does anybody have a suggestion for a better model? Well, I don't know if it's better or not, but. So we don't like nonlinearities. So is there a way of making the problem, and this is not a good thing to say, a little less nonlinear, because you're either nonlinear or you're not. It's not like you can be less nonlinear. Anybody want to make it less nonlinear? Yeah? What do we do? Sorry? Yep, what do we do with the bounds? Okay, yeah, you can deduce bounds on the products x3, x2, x1, x4 from the bounds that you have there. They're big, but
Simply we can add few more variables.
okay, I like adding variables, not too many. How many would you like to add? So go on.
For example, we can say that y1 is x3 by x1.
Okay.
Or in other words, we can say that x1. In other words, we say that x1 y1 equals x3. And
Okay.
similarly, we do y x2. We can say that x4 y2 equals.
Oh. Yep. Y2 is x.
2y x4.
Okay, so let's call it y4.
Yeah. x2 y x4.
Yep.
So that means x4 y4 x2.
Right, and then I would minimize.
We can also have w.
Oh, and w, okay.
And w is y1 y4. The product of y1 and y2.
Okay, yep, and then we would.
We can minimize the 1 by 6 constant minus w squared.
And the constraints would be all those three constraints here that I have here. These two and this one. Yep, and now I have a quadratic model. Yeah, that's nice. This is better than my solution. So I show you my solution, and then we can see if anybody else had my solution. So all I did was I thought, well, I'll just multiply through by the denominator, right? I mean, what am I doing? I'm trying to get as close as possible to 1.6931. So I can just rewrite that saying, well, I just multiply through by y1 minus y1 times y4, which is the denominator on the right, and then multiply through by the other one. And now I can do the same that you're doing, and now I get a better formulation. Now I can say minimize T1 minus 6.931 T2 squared, subject to T1 is y1 times y4, T2, is y3 times y2. And I have one less bilinear expression.
But you have T1 T2 over there. The squared T1 minus 6.931 whole squared.
Oh, that's right. Yeah, yeah. So I still have the same. You're right. Yeah. Okay. We're the same. Okay. Nobody wins. Oh, right. So now I can change my norms. Yeah, we're allowed to do that, right? I mean, look, the modeler wants to get as close as possible to 1 over 6.93. And they choose the 2 norm. But if we do the absolute value, then, okay, so now Pietro has a better formulation, which is, we'll do the absolute value of this guy. And this is now non-smooth, but we can rewrite that objective as minimize S subject to S greater or equal to T1 minus 6.931 T2 and S greater or equal to the negative of that expression. And I apologize that and then these other two constraints. So Pietro wins because he has two bilinear terms and a linear expression otherwise. So round of applause for Pietro, and then go and have some lunch. Excellent, thank you. Oh, there's conclusions here. Domain-specific languages are great, you should use them. Come back the afternoon and learn about them. That's it.